like superlative.
Okay. So if you haven't already looked, there's an exam 1 section. In there, there's a link to a practice exam that I wrote recently, which has a few questions on there. The non-calculator part, yours for real will be much shorter than that. A calculator part, where you get to show me some definite and indefinite integrals. You get to do a Riemann sum for me and take its limit. Double check some areas, track a ball going up and then down, and there's a couple spots where you need to demonstrate the fundamental theorem of calculus for me. The real, ooh, I can't count, 31, 32, 31, 32. The real test will be way shorter, like a quarter of this length. Yes, sir.
So can you go back to the practice exam? Scroll down. Oh, okay, now I remember. So for the Riemann sum, can we use some computers? Like, or do we have to do all of the addition?
Oh yeah.
By ourselves.
I only ask for 4. I think you can do 4, add up 4 things by yourself.
Okay.
Yeah. You certainly can use a calculator like GeoGebra or Desmos to check your sum, but I want to see it. I'm confident you can write down 4 things added up. And notice I don't ask for 100, I just go straight from 4 to n, which means you need to write a formula, simplify the formula using some of these cute little summation techniques, and then hope to be able to take the limit of that. So we can do one of those later. We have at least a day to review. All right, moving on. There's also a ton of extra practice problems if you choose to do them. Neither the practice exam nor the review count towards your grade, but you should do some of each, if not all of the first one and some of the review questions. And the review questions was just me picking problems I thought were cute out of them. They're like a highlight of the homework.
Why do they have to be cute? Why can't they be
Interesting.
Math is cute.
disgusting?
All right, so here we have a homework question that was asked about. I did almost the exact same problem in Friday's video, so if you want to see another version of this, check it out.
You started your recording, Rick.
Yeah.
You sure?
Yeah, I did. I remember I told Sam to behave himself.
Okay.
So I have a problem here in that I have an x inside the root and I have an x outside the root, and the x minus 1 stands in the way of me combining powers. Okay. In the past, we've been able to do things like if we had an x times a square root of x, we were able to write that as x times x to the 1/2, which adds up to x to the 3/2. So I get rid of the product. I can't do that here because the root and the minus are in the way. So substitution is one of the few ways I can handle this. We'll pick up another technique next chapter. I'm going to get rid of that minus because that is the pesky part in my point of view. So I'm going to let u equal x minus 1. So what is du? It's just what?
At 1.
1 dx, right? We're going to write it in differential form when we do substitutions. So then I come back here and I think, well, okay, I have 1 dx for sure, check. I have an x minus 1, I set it up to be that way. But this x on the over there is a problem. I can't mix u's and x's. What's that? You're almost there, Vitor. All I need to do is just kind of clean this up and solve for that x right there. So that means x would be u plus 1. So now I have the tools to get rid of every x in that integral right there. So my new integral, I'm going to pull the 6 out. Instead of an x, I have parentheses u plus 1. Instead of the square root of x minus 1, I have the square root of u. And instead of a dx, I have a du. Now I still have a product, which is a problem, but now I can distribute the root through there. And that's what I needed to do that I couldn't because the minus was inside the root up there. So this becomes 6 times the integral of u times the square root of u plus the square root of u du. Guess what I might do next? Okay, how am I going to simplify? The u times the square root of u is still a problem. Yeah, I'm gonna write that as u to the 1/2 for both of them. Okay, so I'm gonna bring this to a new page. So now I have 6 times the integral of u times u to the 1/2 plus u to the 1/2. I'm getting ready to use my power rule, right? I only have a few limited tools right now. If I multiply things with the same base, I get to add their powers. U has a power of 1, so this is 6 times the integral of u to the 3/2 plus u to the 1/2. Now I can finally come up with antiderivatives after I massaged it into a state where I can recognize a rule. 6 stays outside. The power rule says add 1 to that. So 3/2 plus 1 would be 3/2 plus 2/2, or 5/2, and then divide by that power.
We can just multiply by 2/5.
You could do that too. Yep, I'm going to do that next. And then 1/2 plus 1 would be 1/2 plus 2/2, or u to the 3/2 over 3/2. And because this didn't have any boundaries on it, I got to throw a plus c there.
Oh,
So the act of taking an antiderivative gets rid of the integral symbol, right? Yep, that's the fundamental theorem of calculus in action right there. And then this could be cleaned up just a little bit. So I'm just going to shrink this down so I can clean it up on this page. Everything. So then I'm going to take Sarah's advice, and I have 6 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. You can distribute the 6 through there. Cleans up a little bit, but not a lot. But that's an antiderivative for this function here. All right, let's try another one. This was number 16 maybe in the homework. I lost that page.
Yeah.
Homework, 5, number 16. So I'm going to use a substitution here. Here I have boundaries to consider too, and there's 2 ways to handle the boundaries. If you watched the video from last Thursday, day 7, I'm going to let u equal what here? 2x plus 1, yeah, it's generally u is going to be some inner function, okay? So then du is just 2 dx. And if I rewrite the 14 there as 7 times 2, then I have my 2 dx. So rewriting this, I've got the integral, ignore the boundaries for a moment, of 7 times u got replaced, or u replaces the 2x plus 1 to the power of 6, and the 2 dx is my du, so I just get that.
Don't we have to add a 2 to the outside because we divided?
No, I just rewrote the 14 as 7 times 2,
Oh, I see.
so that my du is 2 dx.
Oh, I see what you did.
Yeah, so I did that instead of dividing. That would be another route though. Yeah, so usually I scan the problem to see if all my pieces are in there. If not, then I fiddle with the data. So there's 2 ways to go from here. One way would just be to find an antiderivative. Okay. And then after you find the antiderivative, you would then reverse substitute. And then you would plug in the original numbers. The other way to do it is to recalculate the boundaries. And then find your antiderivative and just plug in. So there's two ways to go. Kind of depends. Often I go for version 2 of this, which is what I'm going to do now. So I can't put a 2 and a -5 here because those numbers right there refer to x values, and I no longer have x in here. So if I want to put numbers in there, I got to find what u equals. So a little table off to the side, x versus u. If x is equal to -2, then u is going to be what? -3?
Mhm.
And if x is equal to 2.5, I double that, I get 5, plus 1 is 6, u would be 6. So if you want to put boundaries in here, you would have to go from -3 to 6. So you got to be careful with that when it's a definite integral. So now I'm ready to, so I've done my recalculate the boundaries, now I need to come up with an antiderivative. Antiderivative is? U to the 7th, and then dividing by 7 cancels with that one, right? So it's just u to the 7th. Okay. And then we have to consider the boundaries now for u from -3 to 6. Okay, so what do I do with those boundaries next? Which goes first? No.
Six.
The top one goes first, yeah. And I'll show a picture as to why again in a minute. So the 6 goes first. So my answer here is going to be, let's see, 6 was the top one?
Mhm.
So 6 to the 7th power minus -3 to the 7th power. So always the top value minus the lower value when you plug it in. Okay. Since this is a negative base to an odd power, the negative sticks around. So I could clean this up a little bit and say it's whatever 6 to the 7th is plus 3 to the 7th, just because of the algebra of powers. And then plug either one into your calculator, you'll get the same answer. That's what we're looking for in the end here. All right, so just a reminder about why we plug in the top number and then the bottom number, and then we're going to move on. So one interpretation of the definite integral, just review from last week, integral is area. Okay. So if I have some function, f of x, and let's say I'm integrating from some number a to some other x value b, right there. The definite integral finds areas, okay, and it accumulates them, all right? So let's suppose that I have an area function, choose red for the area function, and the area function is going to be equal to the integral from, let's start with 0 to x of f of t, that's a t, dt. And oops, a is a function of x here, so let's clean that up. Okay. So the area function is you just plug in the endpoint, and starting from 0, it will start finding areas for you. Okay. So for example, a of little a, what would that find for me? Well, that would find from x equals 0 all the way up to a, that would find this area right there. What would a of b find for me?
From 0 to b.
That would go from 0 all the way to b, all of that right there. If I wanted to get the difference in between a and b, so if I only wanted the area in here, which would be this chunk and that chunk, when you agree I would take the bigger area and subtract away the smaller area, right? Take the big yellow thing, subtract the little blue thing, and all that's left would be these regions right here. So in the end, that red region would be A of B, that's the bigger area, the righter endpoint. Rightmost, there we go. Better, Sam? Minus A of A. Yeah, so that's why you're going to subtract the right endpoint, which is the upper one in the integral. First start with the right endpoint and then subtract the left endpoint, right? Because we're adjusting for those areas in between. All right, I hope that helped a little bit. Moving on, substitution. Why the hell does it work? Hopefully you watched my video on that, Vitor. You're on a roll today, dude. So it works because of what we know from differential calculus. And half of what we do in integral calculus is dependent on what we did in integral calculus. Okay? So for example, where did we come up with the rule that the antiderivative for x to the n is x to the n plus 1 over n plus 1? Where did we come up with that? We came up with that because we knew the power rule for derivatives. Okay. Substitution is a similar idea. Substitution comes from chain rule. You have a function f of x of g of x. Chain rule says take the derivative of the outer function, leave the inner one alone, multiply by the derivative of the inner function. And anytime you have a derivative rule, you can rewrite it as an integral rule. So the integral version of this right here would be the integral of that thing, f prime of x, f prime of g of x, times g prime of x. You gotta throw that dx in there. Would be equal to what's in here on the other side, f of g of x. So that's where the idea of the substitution comes from. If we can recognize an inner function, then we can substitute it out. So this is my u there, and this is my du right there. That's where it comes from. Okay, so I'm just going to exercise that on a function that you're familiar with. The substitution is a consequence of the chain rule. So check out the derivative with respect to x of the sine of x squared. What's the derivative of that function? Cosine of x squared. Then times 2x. Okay, so based on that, if I asked you to integrate the cosine of x squared times 2x, oops, this supposed to be 2, get the head of my brain, 2x dx, you would say an antiderivative is sine of x squared. Okay. So now we can see that clearly because we have that derivative formula written above. If we didn't have that written above, the trick here is to let u equal x squared. Then du would be 2x, almost dx, right? We write it in differential form. There's going to be a dx somewhere. So cleaning that up, I get the cosine of u, and then here is my full du, right? Exactly as I need it. Now, an antiderivative for cosine of u would just be sine u. And reverse substituting, we get sine of x squared. So that's the power of the chain rule. If you happen to have an inner function whose derivative sort of kind of lives outside, we can drastically simplify it, take the antiderivative, and then resubstitute, and all is good. Yes?
Is there like a anti-power rule?
Is there a what?
Anti-power rule, you know, because there's one. Like
Well, yeah, the anti-power rule is this one right here.
No, sorry, no power. Product rule, like quotient rule.
Oh, product and quotient, yes. I don't think I want to tell you about the product rule today, though. But I might, since you brought it up. Yeah, that actually appears in the next chapter, but it turns out we can use it today.
Way to go,
Okay.
dude.
So we're moving on. Section 1.6. Exponential and logarithmic functions.
This is like calculus 1. I'm just understanding everything.
All right, so think back to Calc 1. The derivative with respect to x of e to the x was equal to
E to the x.
e to the x. So we can say then that the integral of e to the x dx should be
E to x.
the x. And we should technically put a plus c out there.
Wait, so if that's how that works, does the fourth derivative of sine x, is that just sine x again?
Yes, yeah, sine cycles over and over and over.
So like any cycle that we see,
In derivatives occurs in integrals, yes.
okay.
Unless the chain rule gets involved, then it gets messier. If you're missing any part of the chain rule, which we'll talk about. All right, another one. We also know that the derivative with respect to x of the natural log of x is equal to
1 over x.
1 over x. And I just ran myself out of room, so let's condense. So the integral of 1 over x dx is equal to natural log of x plus c. Now, I mentioned this last week. This isn't quite accurate. Maybe remember why this formula isn't quite accurate?
It's an absolute value.
Yeah, I need an absolute value because here I can put a positive or a negative in the bottom, but I just can't put 0. The natural log can't handle negative numbers. So to make them compatible, one way to make them compatible is just to throw an absolute value here. Now they can handle compatible values.
Will that be an issue when we're writing it down in like my old math? Will we need to remember to do that?
Often the problems might say something, assume that x is a non-negative value.
Yeah, I will come up with it.
Yeah, otherwise you might need to put that in there. All right, so I've got a slight dilemma. If I take the derivative of e to the x, I get another e to the x type thing, right? So the integral of e to the x happens to be an e to the x type thing. However, if I take the derivative of the natural log is gone, and I have a 1 over x. So the question is, what if I want to take the antiderivative of the natural log of x? So what that means is I need to think and say, what function could I have taken the derivative of where natural log of x is the answer? Okay, it's not natural log of x, right? Because what's the derivative of the natural log of x? 1 over x, right? The natural log disappeared on me. I mean, shoot. Okay. So I'm racking my brain, thinking back to problems from Calc 1. Man, did I ever take a derivative where the natural log hung around? And Vitor sent me this message earlier in time that said, hey, sometimes when you use the product rule, the natural log stuck around. Oh, you're right, Vitor. So, all right, so if we took the derivative of something like, how about x times the natural log of x? Okay, so product rule, derivative of the first function is 1 times the natural log of x is the natural log of x, plus x times the derivative of the second function, which is
1 over x.
1 over x. So I get the natural log of x plus 1. Oh, so close to a function whose derivative is just the natural log. But I got that pesky plus 1 hanging around.
Is that
Minus
just a
1.
Okay, yeah, so wouldn't it be nice if there were a minus 1 here, right? And there. Okay, so what function has a derivative of minus 1? Negative x. So if there happened to be a minus x up here, then I would get a minus 1 over there, and then I would have just the natural log of x left behind. Accidentally, through trial and error, we find a function whose derivative is natural log of x. So let's rewrite this as an integral formula. Okay, so I got to shrink this a little bit to fit it on the same page.
You're struggling with space.
I'm having space issues today. This is true. Space and time issues, actually, if you want to get technical about it. That's a problem I'm going to take up with Einstein. All right. So then the antiderivative of the natural log of x, or an antiderivative, would be this mess I have here, which is x and the natural log of x, then minus x. Eek. Eek. And then we got to throw in a plus c, you know, there could have been. Okay, so sometimes things get messy. I'll show another way to come up with this formula next week. For now, we're just going to have to go with this messy guess and show answer, which is true, it's accurate, it works. That's the antiderivative. You ask an antiderivative calculator or Wolfram Alpha, it will spit this out as the answer. And so for now, you just have to commit this to memory.
Oh,
since we don't
seriously?
have another, yeah, seriously. Since we don't have another way to do it. Now, we've been committing a lot of things to memory, haven't we?
Yeah.
Yeah, it's just the way of it. I mean, eventually you're going to run out of storage space, in which case we then look it up. Okay, and we'll work on that later too. What's up?
But we have to memorize that one for you.
Yeah, what's the one?
The fundamental.
Fundamental theorem of calculus? Yes, on the practice test I did say, can you state the fundamental theorem of calculus part 1 for me? I also asked if you could state the definition of the definite integral. So those are two things you better write down repeatedly every day until the test.
Wait, what was the second one you said?
I asked for the fundamental theorem part 1, and I asked for you to be able to state the definition of the antiderivative.
Is it the
Sorry, the definition of the definite integral.
Is that
Is that the end?
limit of the Riemann sum?
Yeah, so,
Okay.
yeah, definition of the definite integral is the limit of the Riemann sum.
Okay. So,
Limit of a Riemann sum. Yeah. So I'll review those later. This was in section 1 or 2. Definition of the definite integral, and then fundamental theorem of calculus was section
I watched
1.3.
that video
I'm sorry.
because he says it in
Because
one
it
of
was
the
so
videos.
cute.
In the 1.3 video, I think he was like, memorize this. when you
I
say
did
it.
say that, yeah, when we were doing 1.3, I said that's going to be on the test. Okay. So let's just review some big formulas we know and add some more to it. So one big powerful formula we have is x, the antiderivative of x to the n is x to the n plus 1 over n plus 1. That's a super powerful formula. It's done us a great deal of good. And then that allows us to do negative powers, positive powers, fractional powers, right? That will let us take the antiderivative of the square root, for example, right? Some other ones we have to memorize to make progress here, otherwise we're taking limits of Riemann sums, which I'm sure most of you are not eager to do, unfortunately.
Unfortunately.
Yeah, there was a time in my life where I hated them too. I don't know, hate's pretty strong. Despised.
I feel like it's worse.
Worse.
Okay. Another one, hopefully you've memorized, antiderivative for the cosine is the... Ooh, you guys are having derivative antiderivative problems. It's just the sine, and how can you check that? Well, by thinking of the derivative of the sine, which is just the cosine. So one thing I have to do for myself is every time I take an antiderivative, I look at the result and I take its derivative to see if I go back when I started.
It's the derivative of cosine is negative sine.
All right. Antiderivative of the sine,
Negative cosine.
yeah, this is the opposite of the cosine because the derivative of the cosine is the negative sine, canceling that negative, giving you just a regular old sine.
I did not follow that at all.
Okay.
But like, you know,
The derivative with respect to x of the cosine of x is what?
negative sine.
So it's
Oh, so
when you
to get-
reverse it,
Yeah.
instead of having sine problems.
Like, I
now
knew
yeah,
it-
it's the so all the co-functions had negatives. For integrals, it's the reverse. All the non-co-functions have negatives on them. That's correct.
Oof.
All right, let's see, some other things we've memorized. The antiderivative of secant squared, anybody remember that one? Tangents.
Whoa.
How about, what's that?
Isn't this the same as the Calc 1 stuff? Except that's the.
It's the Calc 1 stuff in reverse, yeah.
It's
Antiderivative of secant tangents?
Secant, that's
Secant.
1 over
Secant.
sine or cosine?
It's
No, 1 over
secant.
cosine.
It's just secant.
Is this secant?
Yeah, because the derivative of secant
Wow.
is secant tangent. It's just secant. Yes. So a lot of the formulas that we have to memorize are just a consequence from our derivatives that we memorized before, even though, winter break, that one thought, and it's a little rusty. How about 1 over the square root of 1 minus x squared dx? Anybody recall that one?
arc sine.
Arc sine, correct.
If you put outside, I
Wait,
could.
while you're ahead.
The other one, this is Lucy.
Isn't it one?
Negative
one-
1 over.
If it was a negative 1
Negative
over, it
one.
would be the arc cosine.
Or it could be negative arc sine.
Or it could be the negative arc sine, that is correct. Yeah, so it turns
Don't
out
say that.
functions can have different looking antiderivatives, and the plus c makes up for that. Yeah.
Why?
Oh, yeah.
Oh.
So if one person takes an antiderivative, it gets function A, and another person takes an antiderivative, and they get function B, and they look different. If you were to add those two things together and do algebra, you would find in the end it would simplify to a single constant.
So how do you know which one it is?
Because they have to subtract them, because they differ by a constant. That's where we get that C. There's multiple right answers. Yeah. So one answer here would be the arc cosine of x plus C. Another possible answer would be the opposite of the arc sine.
Is that true for the other one? Could it be negative arc cosine on the other one?
Yeah, you could call this one the negative arc cosine, correct? Yeah. Yeah.
I just like
Alright,
this.
we just learning how to
That's
undo
just-
everything that we learned.
I told you this
Seriously?
going backwards is a little harder. All right, so two more things you need to add to the list of stuff to memorize.
It's E and U.
What's that?
It's E to the X.
Yeah. So the antiderivative of e to the u du is e to the u plus c.
I like that one.
The antiderivative of the natural log of u du would be, anybody recall?
1 over
u times natural log of u minus u plus c.
that's
There's another one.
There's no chain rule stuff in there? Like we don't have to
Because you said things
multiply
get
anything out?
messy.
Yeah, I'm putting the u in there to justify the chain rule. So for example, if I had
Oh, because
if I had the definite integral of the natural log of x squared was my u, then I better see a darn something like a 2x dx outside, otherwise I can't apply this one. So then here's my u, there's my du right there. So this would just be x squared times the natural log of x squared minus x squared plus c.
Let's see, yeah.
Are we gonna do logarithms?
What's that?
Are we gonna have to learn
Other logarithms?
like log of B?
Yeah, I'll go over those in a sec here.
Don't say that.
Okay, so that's an application there using the substitution or chain rule involved. All right, so Daphne just says, well, what about other bases besides E? And so I need you to reach way back to the middle of Calc 1. What was the derivative with respect to x of 2 to the x?
Oh,
was e to the
You
log.
said that log-
There's a log in there.
Yeah, so it ends up being the natural log of 2 times 2 to the x.
Oh, yeah, no. Yeah.
Okay.
You were way off, dude.
When did you ask us this? Because you asked us that exact question recently.
Okay. So then if I wanted to write an antiderivative formula here, then the antiderivative of the natural log of 2 times 2 to the x dx would just be 2 to the x.
Okay, what's the antiderivative of 2x?
2x. That's different. Hang on, focus on this for a minute. Okay. So sometimes just the 2x will live on that side. So what should I do with the natural log of 2? Divide it over to the other side. Right?
What?
I'm going to divide both sides by natural log of 2.
But
Natural log of 2 is just a constant, true?
Well,
I
yeah.
guess you could, you know.
So that means the antiderivative of 2 to the x dx is equal to
Oh
2
no.
to the x over natural log of 2 plus c over the natural log of 2. Now c is some arbitrary constant,
So you have to know C.
and arbitrary constants are kind of like black holes. They just swallow anything you give it, so we can just still call it c.
Wait, why?
Okay, I'll do it a slightly different way. So c is a constant, right? And the natural log of 2 is a constant, right? So I'm just going to rename that constant k. How about that?
And you just have to memorize that
Yeah. So
K is.
with the derivative formula for some foreign base that's not e, you have to multiply by the natural log of 2. Okay. What's the inverse of multiplying?
Divide.
Dividing. What's the inverse of a derivative? An antiderivative or an integral. So the integral has to divide by the natural log of 2 to compensate.
okay, so you can divide anything inside of the integral as long as it's a constant.
As long as it's a constant.
What
Yeah.
is if it's not?
What happens is not a constant? Okay, let's do that next.
Oh.
Vitor! Come on!
Well, Vitor, if you watched the video on Friday, you would have seen me talk about that very question. What if it's not a constant? All right, and this gets to a question Ben asked about earlier that I just kind of responded to Ben, but the whole class kind of missed that discussion, I think. So consider the, how about the integral of the sine of x cubed times x squared dx. Let's do that. That's rather complicated. I should make it simpler by substituting something out. Yeah. Almost anytime you see a composition of function, substitution should say pop in your head. Might substitution work? The inner function is x cubed, so that's what I would let u be. Du would be
x squared dx.
Not 3x.
3x.
No.
squared.
What?
Dx.
Squared dx. You take the derivative of u times dx.
Okay.
you'll recover. Don't worry. It's all right. Yeah. So remember the regular. What's that?
3 to the outside now.
Yeah. So the problem here is there's no 3 over there. Okay? So there's 2 ways to deal with this. One way is to just remove that 3 from the right, divide it to the left. So then I would have 1/3 du equals x squared dx. So I'm going to have to introduce a third into that problem when I substitute. So now for the substitution, sine of x cubed now becomes sine of u. And x squared dx is now 1/3 du. And you could pull that 1/3 out front if you wanted to. So this could be 1/3 times the sine of du. Right. So now it's way easier to find an antiderivative here. So if there's just a constant, then we can multiply and divide constants all over the place to make things work. So
Just throw numbers around.
I can just basically throw the numbers around. Right. Okay. Now that's if it's a constant multiple. What if it's a variable multiple? So consider the integral of, let's use cosine this time. Oh shit. Oh, I didn't take the antiderivative, so it's okay. Never mind. Sorry, I'm okay. Cosine of x squared.
Okay.
All right. So this is complicated. It's got a function within a function. So I think maybe a U-substitution. U would be what here? X squared. Du is
2x dx.
2x dx. Okay, so there's no 2. That's no big whoop. I can throw 2's around. but there's also no extra x. Oh crap. Maybe I could try the trick from before and say this is 1 over 2x du, which equals dx. Hey, I like that because there's a dx and there's a dx. But what problem have I introduced?
Rational function.
I have now u's and x's stuck together. Because now if I substitute, I get the cosine of u, and then dx becomes 1 over 2x. Yeah.
You had to solve for u of
Or it would be 1 over 2x du.
It'd be du, right?
Du. Oops. Yeah. Sorry.
So, yeah, use the first equation to solve for u.
Oh.
You put it.
D. Okay. I think we're good there.
No.
Kind of. All right. So, all right. So I could try to fiddle with the above. What would x be?
Square root of u.
Plus or minus the square root of u. Plus or minus throws me a little kink. Okay, but I could try it. So this would become the integral of the cosine of u, basically divided by plus or minus the square root of u. And maybe I could assume everything's positive and I don't have to worry about the minus, but okay. Guess what? I'm worse off than when I started.
Why can't we solve for
Yeah,
x
you
and
do this
then
in
plug
the
that in?
video.
I did, yeah. That's what I was trying to tell you earlier.
What?
I did this very problem in the video last week.
Can we not just
Thanks for
solve?
remembering or watching. What, Ruby?
Can we not just solve for x?
Because
I tried solving this for x up here
Is this the one we got?
to get just u.
Oh,
I'm
okay, so you
backtracking to
did-
1.5 for a
you did-
second.
Yeah, okay.
So it's just, there's nothing to do.
So this didn't help. I'm worse off than I was before. Here I had just an x inside there. Now I have u's all over the place.
It's plug
Okay.
So what do you do?
And now think about, remember the quotient rule from Calc 1?
Mhm.
Right? So I have a snippet of a quotient there, not the whole thing. William?
Couldn't you, pull the 1 over 2x outside of the integral?
You can't because x is a variable. You can only pull constant multiples out. That's the catch, yeah. So that's what my point of this was. Constant multiples are okay. We can throw them from side to side. We can pull them out of the integral. We can pull them out of a derivative. Variable multiples are stuck inside. Can't pull them out.
Just say it's 1/2 times 1 over x. And pull up the one, it still doesn't do anything.
I still have an x, right? And now I have an extra u. And so it turns out substitution will not solve this problem. Okay? This is a dead end.
it's a dead end, Ruby. Just
Yeah.
give it up.
And a lot of mathematicians spent a lot of time trying to solve this problem.
The
You
one.
can't solve it like this.
Okay. So if you look this problem up on the internet, let's look it up.
Wait, this is legit an actual like problem.
This is an actual problem, yeah.
Would-
Yeah,
so
I talked about
technically-
problems like this in week 1. Okay, you guys, shh. Your side conversation is disrupting this. Okay. Thank you. So if I go to, let's see, what do I want to look up? Integral of
Oh, you worked out really
cosine
good.
of x squared. Will it give me something? How to take the integral of cosine of x squared. Ooh, interesting. Quora.com. What do they have to say about it?
You can't.
First, taking the integral of cosine of x. So
Sin x is 2x.
So they're trying to say, yep, so
Just the
integral,
antiderivative.
yeah, so this guy's confused. Oh, he's trying to ask about it, and someone's saying, oh, yeah, you could try this. And, you could approximate it
way.
using Taylor series. So here, there's no good, oh, here's an interesting one. They say here it is, the antiderivative of the cosine of x squared is the square root of pi over 2 times this function called c of square root of pi over 2x. What is c? C is the integral of the cosine of blah, blah, blah x squared. Wait, isn't that what I started with?
And now you have 1/2 pi in it.
Okay, so that got
So-
worse. Let's try somewhere else.
If someone solved this, like in actuality and proved it, would they become like a math legend?
Someone's already done it.
No.
Oh,
It's the same thing.
there's nothing we can figure out now.
All right, let me go to Wolfram Alpha. Has anyone checked out the integral calculator yet?
Yes.
No.
Integral of, I'm gonna do sine this
One
time.
time for n1, and I didn't know if it was exactly correct, so.
The answer is, oh, now this function called capital S. What does capital S equal? Well, capital S equals the integral of the sine squared of some
1/2
constant.
pi
So
over
Yeah,
is that
so-
equal as the result started with?
Yeah, so it turns out there is no fundamental function we've seen before that is the answer to this.
But how do you say it's proven?
Somebody proved there is no fundamental antiderivative for the sine of
So
x squared.
there's no answer.
There is an answer, but you can only approximate it with some crazy other math that you might learn about Calc 3.
It's not so nice.
So there are functions for which there is no antiderivative that we know of today. So they give the function a special name, okay?
unsolvable.
Oh, those are the
So what Wolfram Alpha and that other website were trying to tell us is eventually the math community said there is no fundamental antiderivative, so we just created a new function called capital S. And capital S of x is equal to the integral from 0 to x of the sine, and then there's some constant, I think it's the square root of pi over 2 times x squared dx. And they're saying this because there is no antiderivative in terms of functions you guys are familiar with. Are we out of time?
Yes.
Damn. So there are many functions we can find antiderivatives for, but there are also many functions we cannot, which means there's this whole new group of functions that integration opened up for us that we didn't know existed before. Okay. It's related to the idea of, for a long time, people said you can't take the square root of -1. But then someone realized that says, oh, actually that is important to electricity, magnetism, and flushing toilets. And other things.
Flushing toilets.
Yeah, it turns out the way pressure works is related to how magnetism works, which is related to pi. You can't describe that stuff out on.
So I've been working with imaginary numbers.
Every time you
since-
flush your toilet.
Every time I flush my
Yeah,
toilet.
yeah, think
That's
about
just
that.
great.
Great.
All right, so section 5 is just about taking derivatives related to e to the x, natural log of x, and 1 over x. Section 1.7 is about those, remember the arc functions?
Yeah.
Which we've already done a bunch of. So there's really not much new in section 1.7.
Are we having to do cinch?
No, we're not going to do, we're going to do, let's see.
Goodness.
In chapter 2 or 3, we're going to do cinch and coefficient of edge.
That's what I was wondering.
Yeah,
Oh,
we will end up doing those.
just kidding.
Oh, you're right.
Depression is coming.
It turns out those functions are important to like hanging power lines. Yeah.